Thanks a lot. Today we are talking about type checking, and in the area of language engineering we have a lot of checks on things we want to validate and to ensure in order to support users with nice error messages. For example, the most obvious thing are parsing errors when the user types stuff which does not conform to the written grammar. Also, cross-references might not be resolved, then we get some linking errors. And the interesting part for us here now are validations which are specific for the current DSL itself, which we usually write with, for example, TypeScript and not directly in the grammar itself. So, for example, we might have syntactic checks which check some more stuff which is, for example, not covered by the grammar for the first step in order to provide reasonable error messages. Or we could also do on the semantic level some checks which we can execute while the user is typing, which can be done with static analysis. Or we also could check the semantics of the written text by simulating and executing it at runtime. And the type checking we want to discuss about today is at this level, so it covers semantics of the language, but which can be statically analyzed. And the main idea is, usually we have a model or an AST, and we annotate the elements in the AST with additional type information, saying which semantic type this AST has. And then we do some validations on these type annotations. That's the idea of type checking, and we use it, for example, in usual programming languages to show some type-related validations. For example, that in an if condition, that the expression we write down needs to be evaluated to a Boolean value and not to an integer value. Because from an integer value, usually it's not obvious how to derive the true and false. Of course, you can do some stuff like that. Other stuff is like, is a value assignable to a variable if we clearly declared the wanted type for the variable, and stuff like that. We also need type checking for resolving cross-references. For example, when we call a function which is overload, then we need to look at the given arguments to derive their types and to decide which overloaded function we might call in our language. And we also needed to create generators where different logic might be executed depending on the current types. And everything, when it fails, we don't want to have only a no, but the user of the DSL wants to know why are there some type problems. So a no is not helpful enough. And today, in the live demo, we focus on the validation part and on an expression language regarding arithmetics, which is logs, but strongly reduced logs. And in general, the motivation for us to develop utilities for type checking is that we want to ease that in practical language and modeling projects. And since the customers ask for web-based tools and solutions, it must be run in the web nowadays. So the main idea is to ease the application of type checking, and in particular to reuse stuff which is often used or even in any type checking project. That's the reason why we introduced Typir, which is a library for type checking. And the main idea are two things. We provide some core features like checking assignability, doing validations, doing type inference, and so on. And the other part is that we provide reusable types which often occur like primitive types, function types, class types, generics, and so on. In the end, this library is targeted to language engineers, since they are the people who need to realize the type checking for a DSL, and we provide an API for them. So no dedicated external DSL, but API developed in TypeScript. The whole library is developed in TypeScript. It's open source, and it follows a pragmatic approach. We will come to that later. And we are developing for it in the rare open source time since this year by Typefox, the company I'm working for, since we are doing a lot of language engineering. And since we are also doing the language engineering with Langium, we provide also a dedicated Langium binding for it. So what does pragmatic mean? It means we target to solve recurring problems in language engineering. So the aim of the project is not to aim a PhD or to do some formal proofs. So we don't support dependent types, for example, and don't use the rule engine or stuff like that. So the idea is to provide default implementations, for example, for primitives, for classes, for functions. We want to provide default solutions for caching, for secular type definitions, which are surprisingly complex when you are developing it on your own from scratch, and solutions for helpful error messages, for example. And we use an internal type graph for representing the type information which edges between to use graph algorithms to do some more analysis. Okay, since it's developed in TypeScript, it's ready for the web. We can execute it nearly everything in web browser thanks to JavaScript. Thanks to Node.js, we can use it even in command line applications, and with Electron we can also use it in desktop applications, for example in VS Code or SIA, and just by using TypeScript for everything. It's open source. That means the whole development is done in an open fashion on GitHub. It's licensed with an MIT license, which means you can use it even for commercial projects. You can use it in closed source projects. You don't need to pay anything. You don't even need to inform anybody about that. So we are open for contributions and funding. We welcome any ideas on the discussions here in the questions after, and so on. And like your ideas, what do you need for type checking in the web? You might wonder, okay, Typefox is known for Langium, and we use it in combination, but Typir and Langium are independent from each other. There's no dependency between those. So if you have a DSL, you can use Typir for doing type checking. And if you have a Langium DSL, then of course you are using Langium. But to ease the work of Typir, we provide a Typir Langium binding so that you can depend on your Langium DSL project on the Typir Langium binding, because then the integration of the Typir is easier. So that's the relationship between Typir and Langium. So they are in the same domain for language engineering, but they are clearly independent regarding the core. Yes, we provide some default implementations, but each DSL is different. Each type system is different, customers, and other people often have some interesting exceptions and special needs. So the question is, how can we customize it? Because it's impossible to provide one solution for each problem. And there are two main things. We provide the main functionality of Typir with services. For example, that's just an interface for type inference, for checking subtype relationships, for assignability, for validations, and so on. And we provide some implementations for them, which are working out of the box by default. But you can replace the implementations, which is simply done since they are used via the services. And the more easier approach is that you take the default implementation, you override only some parts which should be adjusted. So in the end, by this approach, nearly everything is exchangeable. And you don't need to take care about it just at the beginning, thanks to the default implementations. The other stuff is maybe you need some custom types. And for that, you can register. I mean, you have to implement the custom types on your own, but you can integrate them in Typir by a registry for types and kinds. And our type graph accepts any types as long as you use the same abstract superclass for it. Okay, let's look how that works in practice and how we apply Typir to arithmetic example language, so that you get a glimpse on how this looks like in practice and how it feels like, and so on. Okay, let's just look. This is a view of a user of the language. So it's just, you can do arithmetic expressions and calculations with the language. You have variables and you have functions. So we skipped for the moment lambdas and classes, which are also part of logs, if you know it. So here everything is fine. We have a variable of type number, and when we assign a number, everything is fine. When we say, for example, no, the user typed true, okay, we'll get some information. Yeah, the initialization expression is not assignable to the variable. It's obvious, but if you want to achieve that for a new grammar, then you need to do type checking. Yeah, okay, the same here. Numbers are not, the problems are reported here as well. So it does not fit to Boolean. Of course, we have more. So we have, for example, here the multiplication, which is fine since the result is a number. But when you say the multiplication should be assigned to a Boolean variable, then of course it's not anymore valid. The other stuff is 13 multiplied with true. Okay, it's not supported in the language as well. So the given operands does not match the definitions for the multiplication. It's trivial. You would expect it for everything, but you need to develop it if a user wants to have it in a new DSL. So that's assignability. Other examples are, for example, in an if statement. It's a comparison which evaluates to a Boolean value. We don't know exactly to which, but true or false. When we say we are using a multiplication here, then it's syntactically correct. You could use this expression somewhere else. It's totally fine, but of course here we expect a Boolean value. So, and so on. We have functions which, yeah, for example here, a plus true, that's not valid. If you call a function, where are we here? Okay. So here we get even, I guess, yeah, the problem, sorry. Oh, okay, my demo was not actually prepared. Yeah, here we get a problem, sorry, that the inc function requires a number, not a true and false. Okay, let's look how we achieve that. So now we are switching to the perspective of a language engineer, and we already wrote our grammar with Langium. So that's already done, and the linking, for example, is also done. So now we are thinking about how to apply it. When we apply Typir, then initially we need to provide some default types which exist always.
Could you increase the size a little bit?
Even more, yes. Even more? That, okay, so I guess we don't need it here. Okay, great. Thanks. Okay, of course we have some primitive types, and we define it by we provided somehow a factory for creating primitive types, which we called kind. So they are predefined by Typir, and we use it to just create a new primitive type. And okay, that's the downside. My lines are too long. And we just specify the primitive name here. So please note, this is a name. When we are looking in the grammar, then it's the same name. So in the grammar, it's also number, boolean, or void. But this is a name for the type here type. So what we could do is we could name it to bool, and that would work as well. So that's the difference between language type and let's call it type here type. And when you start with a topic that's a trap you face at the beginning, at some time it's fun for you. And we can do the same for numbers, for voids as well. And we decided to provide the inference rules which define which node of your domain, of your AST, gets which type here type directly together with a type. It's not forced, but you can do it. For example, here it's just when a type in our a node in our AST fulfills this condition, meaning it's a Boolean literal, then this primitive type will be inferred. That's the semantic here, and the other is if we have a node and we don't know which kind of node it is. This means the unknown in TypeScript, so that's TypeScript specific. So then we want to check whether it's a reference to a type and whether it's a name to the Boolean. Here again, the Boolean is a part of the DSL. Yeah, we do it the same for the numbers, for void. And a bit more interesting is how we define operators. So remember, we have these operators, which are plus. Internally, we map them to functions. You could change that. And we have some arithmetic operations, which get two numbers as input and get a number as output. And we define the signature. So on the left-hand side, it must be a type number. On the right-hand side, it must be a type number as well, and the return type is a type number as well. And we have some inference rules. The same principle occurs for our comparison operators, which are here defined for now for numbers only. Just this difference is input is the same, two numbers, and the output is in this case a Boolean. Not obvious, we do the same for the Boolean operations and or. And we have the assignability, which we treat as operators here as well. And here we see we have two ways we could assign a Boolean to a Boolean and a number to a number. And therefore, we provide two variants of this operator. So the first one where both are numbers, and the other one is both are Booleans. Okay. The same principle, but with one operand less, is when we want to define unary operators. Here we have the negation for Booleans, which is a Boolean as output again, and the same for numbers as well. Okay. That's the way here. And we skip some more inference rules from now. They are a bit complex to understand since you need to dive into the grammar a bit more. Let's check. So for now, we defined how the types look like in our type system, and we get a glimpse on how we infer these types. Now let's look how we define that the user gets a validation error when he uses the wrong type here, for example, in an if condition. And we do it by adding a new validation rule, and we check that we get an if statement. The same counts for the whiles and for the fors. And in that case, we have a constraint that we need to ensure that the condition of the node must be a type bool. And we remember our type bool is, go to definition, that's the primitive Boolean type which we initially defined in Typir in our type system. Okay, now. And in this case, we provide if the condition is not assignable to true to Boolean, then we provide the message conditions need to be evaluated to Boolean, and we see it here. Conditions need to be evaluated to Boolean. So we can directly customize the messages here as well, and we can even define that the condition itself here is marked, and for example not the whole if statement, because that would be here 7-8 lines. So even here some customizations are possible. That's a strategy in general. Let's do something more. We have, for example, also a print statement, and here we have no strings, so therefore at the moment print is supported for everything, and we can print numbers. We could also print booleans, and when we want to say for some reason Boolean values shouldn't be printed, then we can add a new validation. We check whether our current node is a print statement, and in that case we say that we need a constraint. We want to ensure that, we could say, for example, only numbers are allowed, is equals, so ensure that the node is equals, and we need to check the value which is returned, which is printed. It should be of type number, and then we could define the details of the message. For example, we say that only numbers can be printed. Yeah, so print, and now we get this nice error message that only numbers can be printed. Oh, I forgot this one. Another often question is, often this plus operator is quite interesting, because, for example, when we are working with strings, then 5 minutes, okay. Okay, we talked about that, then let's say, what about overloaded functions? So a function with the same name but different arguments. Okay, let's copy it, and we see declared functions need to be unique. I just copied it. It's everything the same, so we have a validation for that as well, which is built in. It's also fancy because now the signature is different, but but it's still not unique, because when you call it, the input arguments need to be different. The output type is not enough. So let's do it. Okay, Boolean, that's fine. Now this one does not work anymore because it's a number. Let's say A. Right. Thanks.
But does this imply that you also do name resolution? Because you have to choose the function based on the type, and the type of the result is again, so it should be integrated with name resolution.
Yes, when you call it, for example here, then of course the name must be taken into account as well. Yeah, you are right, I said only the input arguments, but the name must be the same.
Resolve the inc name to a certain function.
Yes.
Meaning
and that's possible here now as well. That's also built in.
It shouldn't work. Give an error because inc2.
All right. I guess I got the message that the language server crashed. Let's try again. Now we have it. Yeah, thanks. It matches only partially, and yeah, for that case, we could say the plus is maybe a bit more. It's not that strict. Then we could add another signature for that. And we already saw these core functionalities which are already implemented, and some default types. We are in an early state. We plan to release the first version in November and are adding more features. We are also interested to support more bindings. So if you have some idea or want to contribute, we are happy. And of course, there are lots of features which could be implemented as well. And in the end, to conclude it, the idea of Typir, the benefits we want to achieve with it is to reuse and to solve problems which occur often. For example, cyclic type definitions, caching for performance, error messages we saw together that needs to be solved all the time. We want to save time for that. We have the bindings for Langium we saw, and nowadays everything must be in the web. And now we are looking for your questions, for your ideas, for your contributions now or later. Thanks.
We have about 2 minutes for questions. If you can set up already, then. So questions. Anna.
I'm not sure the performance. Is it the incremental? Is it, let's say I have a big repo, everything is type checked, I modify one file, does it retype everything, or it's typing this file and the dependent files?
In the end, it depends on how you integrate the type checking in your DSL, which usually depends on your language workbench. For example, Langium is not incremental, so it's parser-based and reparses the file anytime you type it. For this file, you need to recreate the types, of course, always from scratch, and the binding takes care that the derived user types, like the functions, are skipped and the new ones are added. But all the other types you don't need to create, and Langium somehow keeps them. So it depends on the how you implement it. In general, a type here can be used in an incremental way by adding and removing types.
If I would want to use this with an Xtext language, how would that work? I mean, your example was with Langdev. I saw very specific is operators and all, but I guess there would be much more work for.
Yeah, but the work depends on, since this is TypeScript and the others is Java. So in general, the data structures you throw in don't matter. So at one place we saw unknown. That's you can insert anything. At the moment, as long as it is TypeScript or JavaScript at runtime. Yeah.
Very last question.
Yeah. You mentioned default functionality. If I have a Langium
Initially, when you just plug it in, nothing. So you need to explicitly tell the type system, Typir, which types you have, for example, which primitive types you have. Of course, you could throw AI on the problem and try to guess which types are defined in the grammar, but by default, the language engineer has to declare it. But then he gets this support for that after doing that.
Let's thank the speaker again.
Okay.